Here's an example of a question 11 out of 25. We're going towards the middle now of AMC 8. Suppose you have two groups of friends who are going to watch a movie. The movie ticket costs a whole number of dollars, but it's more than $1. In America, you can't see a movie for $1 or less. One group spends a total of $143. The other group spends a total of $221. How many people were in the first group of friends? When you first look at this problem, sometimes it seems like there's not enough information. We don't know anything about how much the movie ticket costs, other than it's the same cost for both of the groups. The key word is whole number. That means it's a number theory problem. It has to do with divisibility. So at that point, we want to think about our friends, the numbers, and the primes, and all of the numbers that multiply to each other. What this means is that the cost of the movie ticket multiplied by the size of the first group is 143. The cost of the movie ticket multiplied by the size of the second group is 221. So that means I might want to know how to factorize 143 and 221. Let me remember that in this way. I know that 143 equals the movie price times the number in the group 1. And I know that 221 is equal to the same movie price times the number in group 2. And so I want to know how to factorize these numbers. 143, you try all your divisibility rules. Is it divisible by 2? No, it's odd. Is it divisible by 3? 1 plus 4 plus 3 is 8, not a multiple of 3, so it's not divisible by 3. I just use a divisibility trick for 3. Or you could have just tried. Is it divisible by 5? No, doesn't end in 0 or 5. How about 7? You try. 7 times 2 would make 14. So 7 would give you 140, not 7. The next prime is 11. So if we try to divide 143 by 11, actually it works. 143 divided by 11, if I take a 1 here, 11 minus 33 becomes 3, 33, and it's clear. So we have that 11 times 13 is 143. Let me share with you a very nice trick of multiplying by 11. Actually, when you multiply any number by 11, for example, 13 times 11, look at how the multiplication looks. 1, 3, 1, 3. And so when I multiply, look, the 3 is here and the 1 is here. That's your 13. But what goes in the middle, you're going to add together 1 and 3. So this is 1 plus 3, which is 4. Whenever I multiply a two-digit number by 11, I put the two digits here and I put the sum in the middle. I sometimes have to carry also, but that doesn't happen here. Actually, if you know that, when you look at 143, you can also see that it's divisible by 11, because 1 plus 3 is 4. That's actually how I would have done this question the first way, the fastest way. Okay, so now I know 143 is going to be 13 times 11, 11 times 13. Okay, but now I know that I need to have some common factor with 221. At that point, now I remember I have this way of multiplying things by 11. How could I make 221? I would get 1 to have 1 plus 1 to be 2. So that wouldn't work very well. If I have a 1 here, the only way I can put a 2 there is if this was also a 1. So I already know now that 221 is not a multiple of 11. So let's go straight and take 221 and divide it by 13. Times 1 is 13. This is giving me 91. And remember, this was our friend. 13 times 7 is 91. Clear. I actually knew that it had to work, by the way, because I knew that this would have to split, and that's where I'm using the fact that no ticket can be $1. Because I cannot say that 143 is 143 times 1. I guess it could have been that there was one person who saw a $143 movie. It's a very expensive movie. But that would have not worked, because then this other group wouldn't have been able to do it either. So now I know this works, and this is going to be 13 times 17. So the common part in both of these has to be the 13, and so that means that the movie price is 13, and the first group has 11, and the second group has 17. And so that means that the answer to this question, number 11, is that the number of people in the first group of friends is 11. Okay, that's nice. But I wanted to share more in this problem. These numbers are picked very carefully, not only to show some nice coincidences in multiplying, but also 143. Is that very close to a number? We talked a lot about a number called 144, which was 12 times 12. Actually, since it is just 1 less than 12 times 12, there's one way to see the factorization of this. 143, we knew, was 12 times 12 minus 1. Oh, that's 1 squared. There's a difference of squares factorization formula, where you can say this is 12 minus 1 times 12 plus 1. So that actually gives you 11 times 13 in one shot. 221. Well, 221 is close to another very important number, which I haven't talked about yet in this sequence. But 221 is actually very close to 15 squared. It's 15 squared minus 4, which is 2 squared. And if you factorize that, you get 15 minus 2 times 15 plus 2. This is actually your 13 times 17. And the last piece I wanted to put on this question is actually there's an even deeper way you can do this, which I don't expect that everyone watching this lesson knows, but I'll say if you're curious, there's a class on number theory, which would actually explain this in much greater depth. What we are looking for here actually is a common factor between 143 and 221, the same factor twice. So it's actually very useful to try to work and calculate the greatest common factor, greatest common divisor of 143 and 221. And there's a method here which is called the Euclidean algorithm. And I'm going to do this fast because I will not have enough time to explain it in detail, to teach it completely in detail. Euclidean algorithm. I don't have enough time to teach it completely in detail in this problem discussion. It's in a number theory course that we have here. But instead what I want to do is show you how fast it can operate if you know what it is. And this lets you take 143, 221 and replace the GCD by keeping the smaller number and replacing the bigger number by the difference between the bigger and the smaller number. So let's just calculate the difference. 221 minus 143. If I subtract, 11 minus 3 is 8. 11 minus 4 is 7. 78. And then that's equal to, again, GCD of keep the smaller number, take the difference between the bigger number and the smaller number. 143 minus 78. 13 minus 8 is 5. This becomes 13 minus 7 is 6, 65. Equals the GCD of keep the smaller number, 65. Replace with the difference between those two, which I now can see is 13. And at this point, you can actually see 13 times 5 is 65. So we get all the way to 13. This is extremely powerful because I don't have to do any guessing at all. This, in the end, shows a number of different approaches to do this. This is a more advanced method, which shows why it's powerful to learn this number theory. But even if this thing didn't make sense, there are other ways to go about thinking of this, from algebra to basically trying to remember these interesting ways to multiply numbers by 11, so you can prime factorize these large numbers. And so in the end, what you find out is that this problem, which is really a number theory problem, has enough information to conclude that the number of people in the first group of friends was 11.